Welcome to Calculus 2. Assignment 1 has just gone out. It's due next Monday. Question 2 on that assignment deals with the continuity of a piecewise defined function. It's on the assignment, and it's also a very popular question on the Calculus 2 exam, and generally poorly done. The question in front of us here is taken from a Calc 2 exam. It was worth 10 and the average mark was 3. So I want to go through and give you a template about how to answer a question like this well and comprehensively. Hopefully that'll help you with the assignment and also with any exam questions if they happen to come along. So here it is. It's saying determine all the values of a and b so that this function is continuous everywhere. The function is equal to the cosine of 2x plus b if x is strictly less than 0. It's equal to this quadratic, x minus a squared, for all values between 0 and 1, including 0 and 1. And it's the log function, which is the log of x if x is strictly greater than 1. So the first thing I want to do is make sure that you really understand how this piecewise function definition works. So of course the function cos 2x plus b is a perfectly well-defined function for all values of x. So I can give that a name. Let's call that g. g of x, and that's going to be the cosine of 2x plus b, and it's defined that way for all x values. Okay, and I can also consider this parabola. This parabola is perfectly well defined, so let's call that h of x. That's x minus a squared, and it can have those values over the whole of the line. And the log function is the final one here. Let's call that k of x is log x. I can't take the log of a negative number, so I can't have the full range here, but that's certainly defined for all values of x greater than 0. And the function f is taking pieces of these functions here, and there is a little GeoGebra applet which will be on the website that you can play around with yourself if you wish, just to sort of illustrate the piecewise nature of this function, and that's shown here. So just as I drew them out with their colours, cos function is blue, the parabola is red, and the log function is green. That's the colours of the functions here. And I can change the parameter. So this is the cosine function. If I change the value of b, I can see that effectively all I'm doing with the cosine function is actually translating it up and down on the line. Okay. If I put b equal to 0, then this is just the cosine of 2x. So it's equal to 1 at 0. Okay. If I make b positive, you can see actually by making b positive I translate the function in the opposite direction, to the left. And if I make b negative, then I translate it to the right, which is something you should be familiar with by considering graphing f of x minus a and comparing it with f of x from school. Okay, so this b parameter is simply translating the cosine function up and down on the line. Now I've also got the parabola here. This is the parabola x minus a squared. So if you remember your quadratic formula, you'll see that it actually has an axis of symmetry at a, at x equals a, and its value is 0 there. So of course if it's x minus a squared and a is 0, that's just the parabola y equals x squared, and so on. Okay, so when I change a, what that does is it moves the parabola up and down in exactly the same way as was happening with the cosine function. And the log function here doesn't have a parameter in it at all, so it's just the stock standard logarithm function. The log of 1 is 0. The log of a number between 0 and 1 goes off to minus infinity, but not very quickly, and the log of a number bigger than 1 is positive, and it increases rather slowly. Remember, the derivative of log x is 1 over x, so the slope here, for example, you can see it's a slope of 1, because that's 1 over 1, so there's a slope of 1 for that function there. Now the piecewise function f, the black one, is defined as being equal to the cosine below 0. Between 0 and 1 it's going to be the parabola, and then above 1 it's going to be the logarithm. And we can show it just by clicking on here, and it's shown in black. So that is my piecewise function. It's just picking out the cosine function below 0, it picks out the parabola between 0 and 1, and it picks out the log function for values above 1. And you can see at the moment with the values of a and b that I have, we have discontinuities here. So you can just play around with this by dragging this up and down. And you think, well, how can I get the parabola to be smoothly connected to the log function? Well, it looks like the only way I can do that is to actually make the parabola touch the x-axis at 1. So a has to be 1. It's pretty close there. And then here you might say, well, how can I get the cosine function to meet the parabola? Now, if the parabola is 0 there, it turns out that it's exactly 1 here. And the cosine does reach 1 at a number of points. Okay, so b equals 0 will do. And you can see there, the black piecewise defined function is nice and continuous everywhere. So we're going to have to deal with the continuity of this function within the 3 regions, and we're going to have to pay particular attention to what's happening with continuity here. And because it's piecewise defined, we're going to have to consider one-sided limits. We're going to have to look at what's happening with this function as we approach 0 from above, and what's happening with it as we approach 0 from below. And if we want to get a limit, we're going to have the left and the right hand limits to be equal. So that's the idea, and you can play around with that applet as much as you like. I don't want to take too much time on this video, so what I've done is I've written out a complete solution. This is a 10 out of 10 solution to the problem. And the first thing we do, because we want to establish continuity of the function everywhere, is we deal with the regions where x is less than 0, strictly between 0 and 1, and then bigger than 1. And then here we deal with those 2 points, 0 and 1, where we've seen that the values of a and b might affect continuity. And we're just going to quote from the results that you have in your lecture slides. So for x less than 0, f of x is continuous because it's a composition of 2 continuous functions, namely the polynomial 2x plus b and the trigonometric function cos x. And this isn't affected by the value of b. Okay, and how do I know that the trig function is continuous and the polynomial is continuous? Well, here's the slide. It's slide 27, continuity theorem 3. It tells you the following function types are continuous at every point in their domains: polynomials, trig functions, exponentials, logs, and so on. So I'm using that part of your lecture notes to do that. And then strictly between 0 and 1, strictly between 0 and 1, the function is equal to this parabola, which is a polynomial, and so it's continuous for all values strictly between 0 and 1, and the value of a does not affect that. For x strictly greater than 1, it's the logarithm function, and the logarithm function is continuous. We're quoting the result from the lecture slides. So now we have to deal very carefully by taking those one-sided limits with the continuity at 1 and 0. And I'm not going to, I don't think, read through all of the detail of this, right? It's just important that you realise that for the function to be continuous at 1, it has one functional form below 1, which is the parabola, and it has a second functional form above 1, which is the log. So you have to consider the one-sided limits. For the limit to exist, the 2 one-sided limits have to be equal, and for it to be continuous, the 2 one-sided limits have to equal the value of the function at the point. And if you look at the function definition, you'll see the value at 1 is given by plugging x equal to 1 into the parabola, x minus a squared. And so when you work this out, you can see, as we saw when we were playing with the GeoGebra applet, that the only way the function can be continuous at 1 is if we set the parameter a to be 1. That is the only possible value of a. Then we do the same thing over here with cosine. So for example, here when I evaluate these limits, I have to quote that I'm using the continuity of a polynomial, I'm using the continuity of log. When I'm taking the limit at 0, I've got the limit as x approaches 0 from below of a cosine. The cosine is continuous, and so I can switch the function and the limit, and I get this value here. And so for it to be continuous at 0, the left-hand limit has to equal the right-hand limit, which has to equal the function's value at 0, which is 0 minus a all squared, it's 1. And when you work through this, you'll see that what you need is that you need the cosine function to be at 1, okay, as we saw here, right? A has been fixed at 1, the parabola is fixed at 1 at 0. We need to find a value of b so that the cosine is 1 at 0, and you can see that b equals 0 will do, but of course, you know, this is a periodic function here. Okay, it works to b equals 0. If I translate it to the left by adding 2 pi to b, there you go, there's another value of b which works. And of course, if I take b back through 0, here it is at 0, and now I translate the function to the right by taking 2 pi off, then I get another value. So all these multiples of 2 pi radians either side of 0 will do. Okay, so these are all the possible values for b down here. What have we done? Overview. We've established the function is continuous within each of its individual regions, less than 0, between 0 and 1 and greater than 0. Then we've looked at the discontinuity points affected by the parameters a and b, and we've made sure that the left and right hand limits are equal to the value of the function at the point. That's the definition of continuity. So that's why you have to use it. And so we've got the values for a and b. And then finally, you should tie it all together. A nice conclusion. Therefore, the function f of x is continuous for all x in R, provided a is equal to 1 and b is some multiple of plus or minus 2 pi.